So we were talking about linear systems. There are unknowns and variables in the linear system, and like taking some numbers along with these linear systems, we like write them in form of an equation, and many equations like this together they form a linear system. And we assume that the number of unknowns is n, and the number of equations is m, right? So n and m. This is the number of equations and the number of unknowns. Now, what we did is that we took the linear system and we created what is called an augmented matrix, right? An augmented matrix, right? This augmented matrix is nothing but we what we do is that we write it in a matrix form, right? And we draw a line, right, just before the last column. So this last column is the right hand side, right? RHS of each equation, right? So the RHS of each equation is RHS of each of the equations, they have some numbers. So those numbers are all written here. So there are a total of m such numbers, right? So the number of rows will be m rows. And in the left hand side of our matrix, right, of our augmented matrix, what do we write? We do write down the coefficients, coefficients of coefficients of unknowns, right? In the of each equation. And while writing them down, what we do is that we use the first, let's say the first column for the first variable or the first unknown, second column for the second variable or second unknown, and so on and so forth. The last variable will be for the last column, correct? And in total, there will be n columns, right, on the left hand side. So if we try to like look at the size of the augmented matrix uh, has got m rows. The number of rows is m rows, and it has got n plus 1 columns, right? So each of these n plus 1 columns represent each of the unknowns and the RHS as well. Okay. Now, having said that, let's move on to a few more procedures to solve this particular linear system of equations, right? So, what we have studied till now is we have from the augmented matrix, we have tried to convert this augmented matrix into an echelon form. And how did we convert this into an echelon form? By using elementary row transformations, right? Elementary row transformations. So these row transformations, again, we can exchange a particular row, we can multiply a particular row by a number, we can add a multiple of one row by another row, right? So there are a good number of possibilities of elementary row transformations that we have come across, and we'll use these elementary row transformations to get what is called an echelon form, right? So this is an echelon form. Now, this echelon form is an important understanding. We should really like not miss out the meaning of an echelon form, because whatever we do further in today's lecture, and also what we had done in the previous two lectures, we had to find out the echelon form and investigate the number of non-zero rows, right? Okay, so let's go ahead and see what we are going to do today, right? Now, today we are going to learn about two different methods. The first method is called the Gauss elimination elimination method, right? And the second method is called the Jordan Gauss-Jordan method. So I hope that you are all taking your notes, right? It's very important that you have your notebook by the side of you with a pen and like keep on writing. Okay. So what we did till now is that we identified, we kind of revised what we have been doing over the past few weeks, right? What we have done in the past few weeks is that we have understood what a linear system is. A linear system has got unknowns. There are n unknowns, and there are m equations. Now each of these variables will have some value, right? And that's what finding out the solution means. We have to find out what is the value of x, what is the value of y, and so on. Now in order to do that, we represent the linear system in form of an augmented matrix. In an augmented matrix, we have got m rows, each row corresponding to each equation, and n plus 1 columns. So the first n columns will be corresponding to the coefficients of each of the variable or the unknown in each of the equations. And the last column will be representing the RHS of the equation. Okay. Now, once we get the augmented matrix, we find out what is called the echelon form by using elementary row transformations. Now, today we are going to explore and find out how to how to calculate the solution. So of course, like whenever we are talking about Gauss elimination method, Gauss Jordan method, we are attempting to find out the solution to this particular linear system. Okay, so we'll start with the Gauss elimination method, right? And today what we'll do is that we will kind of take an example and try to solve the example and see how this method works, right? Okay. Now, is everyone there? Can I see a thumbs up on the chat box from everyone, or maybe you can react? Okay, okay, okay. If do let me know if I'm going too slow or too fast, right? Okay. Great. So what we do here, in a nutshell, we write the augmented matrix, right? We write the augmented matrix, and we use row transformations to get to an echelon form. The echelon form, it is we are going to loosely use the word echelon form today, but what essentially I mean is that we want to get the augmented matrix in the form of an upper triangular matrix. Upper triangular matrix. Now, what is an upper triangular matrix? We all know that if we have a matrix, right, and uh, the element in the first row, first column, the element in the second row, second column, third row, third column, and so on, they form the diagonal of the matrix. So, an upper triangular matrix means that every one below the diagonal, they are all zeros, right? Everyone below the diagonal are zeros. On the diagonal and above the diagonal, they can have any non-zero values. We are not bothered about them. We are only interested in seeing that the elements below the diagonal are equal to zero. We want these elements to be equal to zero. And when we are finding the echelon form, that's essentially what we are trying to do, right? We are looking at non-zero number in the first row, first column, and below that we are making everything zero. Then we'll be looking at the second row, second column element. If the second row, second column element is a zero, we move to the third row, third column element, right? And whichever diagonal element is a non-zero number, Below that, everything, we want everything to be 0, right? So in the Gauss elimination method, this is essentially what we are trying to do. This is what we are going to do today, right? We are not going to find out the rank. Yes, someone was picking up. Yes, Rahul. It can be 0 as well. No problem with that. We'll see how to deal with it when it is 0. Okay. There are some other people who have raised their hands. Prisha, Naman, Naman, you have got a doubt. Mahalinga, you have got a doubt. Okay. Okay. So let's take an example, right? Let's take a system of equations, right? And try to solve it using Gauss elimination method, right? So, so let's see what question we can have, right? So the aim is to achieve an upper triangular matrix. So let's try to solve a particular system, right? We'll write it down, maybe x minus twice y plus 3z is equal to 2, right? And then there can be another, let's say 3x minus y, then plus 4z is equal to, let's say 4. And then the last one, we can take it as maybe 2x my plus y minus 2z, right? This would be equal to 5, right? So we have got three equations here, and we want to solve this set of equations. Now, in school mathematics, what we had done is that we had written x on the left hand side, taken everything on the right. In the second equation, we substituted that value for x, and x is eliminated, right? So we'll have the second equation in terms of y and z, and then we write y on the left hand side and everything else on the right, and then substitute that value in the last final equation, and then we get the value of z. And then we substitute the value of z in a relation where y and z are there together. We find out the value of y. And once we get the value of y and z, we find out the value of x. So this is what we have done. But it is very calculation intensive. That's the reason we could not, like that's the reason we want a smarter method of doing it, right? Because just imagine there are 5,000 equations and, like, let's say 2,000 variables. So, like if we have a matrix, if we create an augmented matrix and find out the rank of it, then we'll get to know whether there is a solution or not. If there is a solution, we can find it out using the matrix method. And Gauss elimination method proves to be a very useful method in solving this kind of questions. So let's get down to the solution, right? And firstly, we need to write down the augmented matrix, right? Now this augmented matrix, how do we write down the augmented matrix? First, we draw these lines there, the boxes. Then we write this straight line, correct? Then, with a light color, or maybe let's write down x here, y here, z here, correct? So what are these? This first column will write down the coefficient of x. The second column will write down the coefficient of y. The third column will write down the coefficient of z. So we'll write down all these coefficients. So the first equation will be the first row, right? And then we'll write down the first row as, okay, someone is trying to say something. Maybe I'll respond to you later, right? Um, okay. Yes. So the first equation, let's write down the first equation. The coefficient of x is 1. The coefficient of y is -2. The coefficient of z is 3, right? And on the right hand side, we have got 2. So the first equation is done. Equation 1. Now let's write down the second equation. The second equation, the coefficient of x is 3. The coefficient of y is -1. The coefficient of z is 4. And on the right hand side, we have got a 4. So this is equation 2. And finally, the last equation, the coefficient of x is 2. The coefficient of y is 1. The coefficient of Z is -2, and on the right hand side we have got a 5, right? Okay. So this is what we have. The first column. How many columns are there? There are four columns. 3 plus 1. There are 4 columns, right? How many rows are there? There are 3 rows. Each row corresponds to each of the equations, right? Okay. The last row corresponds to equation 3. Up to this, we are all very clear. We should not make any mistake here, right? Now, what we want to do is we want this 3 in the second row, first column, third row, first column 2, the third row, second column 1. All those highlighted numbers, we want all of these highlighted numbers to be equal to 0, right? We want all of this to be equal to 0. Now, let's get down to work, right? And let's say what is the operation, right? So, in order to make this 3 to be equal to 0, we need to change R2, correct? We can write R2 as R2 minus 3 times R1, correct? So, what is happening? When we are doing R2 is R2 minus 3 into R1, R2 element is 3 minus 3 times the R1 element is 1 for the first column, right? And hence we are going to get a 0. Okay. Now let's write down the first row. We are not changing anything in the first row. The first row is 1, -2, 3, and then we have got a 2 at the end, right? We are not changing the third row as well. The third row will be 2, 1, -2, 5. However, we are changing the second row. So second row, the first element is 0. The second element will be as follows. We'll write it down on the right hand side. So the original element is -1 minus 3 times of -2. This is R2. This is R1, right? So we get -1 plus 6, which is equal to 5, right? So we write 5 here. Okay. Now, um, Now we'll look at 4, right? The third column, we have got 4 minus 3 times 3. This 4 is the value at R1. This 3 is the value of R2, right? And then we get 4 minus 9, which is equal to -5. So we write -5 here, correct? Okay. Now we look at the last column. In the last column, we have got 4, right? Minus 3 multiplied by 2. For that, you have to look at the previous matrix, correct? In the previous matrix, in the last column, the R2 value, pardon me, the R2 value is 4 and the R1 value is 2, correct? So that gives us 4 minus 6 equal to -2. That's equal to -2. That is equal to -2, right? So we have got the second row in which in our desired format. What is the desired format? Desired format is that the second row first element should be 0. That element we have got as 0. Okay. Now let's convert the 2, right? There's a 2 value 2 there. Correct? I'll highlight that with a yellow or with a dark color, right? So this 2, we want to convert this 2 into 0. Now how do we do that? Again, R this 2 remains is this 2 is in the R3. So we are going to change our R3 as R3 minus 2 times R1, right? Now what will happen here? The number 2 will be the R3 element, right, in the first column, minus 2 times the R1 element is 1. So 2 minus 2 will get that as 0, correct? So let's write it down. The first column, the first row and the second row remain the same, right? -2, 5, 3, -5. Then there is this line. 2 minus 2. We'll edit the last row, right? Last row for the first element is 0. So the second element, it was 1 previously, right? So R3 value is 1 minus 2 times R1, right? So the R1 value is negative 2. So this gives us 1 plus 4, which is equal to 5. So we'll write 5 over here. Further, what we'll do is that we'll look at the third row, third column element. So originally the third row, third column element was minus 2, right? Negative 2 minus 2 times the first row element, R1 element. So R3 minus 2 times R1. So R1 element is 3. So you get minus 2 minus 6 is equal to minus 8, right? So minus 8. Finally, the third row element of the fourth column was 5 originally, right? So R4 R3 minus 2 times 2, because 2 is the R1 element of the fourth column. So what we get is 5 minus 4 is equal to 1. So we write down here 1. Okay, it's pretty straightforward. It's a little calculation intensive, but it's better than, there are no variables, no unknowns here. These are just numbers. So any mistake that you might, like have you make here would be nothing but, very small silly mistakes. So you can always go back and correct your mistakes. Okay. Now yes, please. Yes, please. Who is this? Yes, Rahil. Tell us. Absolutely. The entire thing will change. The right hand side is also going to change. Together we are going to do. It is a matrix, right? Because why it is going to change is because when each row is each equation. So let's say if you want to add two equations, right? Let's say if you want to add two equations, uh, let's choose this color. So let's say we have got 3x plus y is equal to 3 and 2x minus y is equal to 2, right? So when you add these two, we'll add the left hand sides and we'll add the right hand sides as well, right? So when you add the left hand sides, we get 5x and that is equal to 5. So we are adding on the left hand sides as well. We are adding on the right hand sides as well. So each of these equations, mind it that each of this equation is one row. This is one row, this is another row. So whenever we are doing some calculations, we should consider the right hand side of the line as well. Does that make it clear? Okay, cool. Now let's summarize where we are, right? Let's get a status update. So the status update is that we have got a 0 here. We have desired that. We have got a 0 here as per our desire, right? So initially when we had drawn the augmented matrix, we had 3 spots which we wanted to be equal to 0. As of now, we have reached 2 of them. The only one that is left is this 5. So we somehow need to change this 5 to 0. This 5 we need to make it to 0. Let's do it then, right? Now let's see R3 minus R2. Exactly. Let's do that. R3 minus R2. So we'll do one thing. We'll write R3. The new R3 is same as is going to be transformed to R3 minus R2. So when we are doing that, R2 and R1 are not going to change. 1 minus 2, 3, 2. 1 minus 2, 3, and 2. Correct? And then 0, 5 minus 5 minus 2. 0, 5 minus 2. Is it minus 2? Minus 5 minus 2. My bad. Okay. Minus 5 minus 2. And then we have got a 0. Okay. R3 minus R2. R3 minus R2, right? So 0 for the first column, right? For the first column, right? it will be 0 minus 0, which is equal to 0. Right? For the second column, right? So the second column, I'm writing in the bottom right corner of the screen, referring to the top part of the screen. Okay. Okay. For the second column, R3 is 5 minus 5 is R2, which is 0 again. For the third column, right, what we're doing is negative 8 is R3 minus negative 5 is R2, right? And that will give us negative 8 plus, yes, minus 3, negative 3. And for the fourth column, let's see, let's scroll up a little bit. Let's see. We have got R2 as minus 2 and R3 as 1, right? So, and we have to do R3 minus R2. So, we have to do 1 minus negative 2. 1 minus negative 2 is equal to 3. Okay, so let's write this down. We have got 0, 0, negative 3, 3, right? Okay, and let's see whether we have reached our aim or not. This is 1, 0. This is another 0. This is another 0. So we have got our all zeros together, right? So all our zeros are here. That's amazing, right? So we have reached the position when we can, like utilize the concept of Gauss elimination method. Okay. Now, uh, now what to do? Now what to do? Very, very important step. We're going to write this step now. So what we do is that we look at the last row. In the last row, before the line, we have got one number. After the line, we have got one number. Correct? Now, before the line, the number corresponds to the third column. So this column is the Z column, right? This column is for the Z column. So we reconstruct the equation from the third row. From the third row, we reconstruct the third equation. The third equation is reconstructed. How do we do that? The coefficient is negative 3. This is the coefficient. Coefficient multiplied by, what is the unknown? The unknown is Z. This is the unknown. And what is there on the right hand side? We have got 3, right? 3 is there on the RHS. So basically, we reconstruct this as negative 3Z is equal to 3. And from here, if we divide both sides by negative 3, we get Z is equal to negative 1. And that is one of the solutions, right? We have got the value of Z. Again, what did we do again? What we did is that we looked at, okay, so we looked at the last row, the particular row where there are only two numbers. One number, there is only one number before the line. What is that number? Negative 3. So negative 3 is going to be the coefficient. This negative 3 is found in the Z column, right? The first column is X column, the second column is Y column, the third column is the Z column. So the unknown is Z. On the right hand side, we have got this number called 3, right? So we write down 3 as, like giving an equal to symbol in between, we write down 3. And this gives us negative 3Z is equal to 3. From there, we find out the value of Z as equal to negative 1. Now, we'll do the same thing. Same thing we'll do for the second column, as for the second row. In the second row, 5, negative 5 and 2 are the non-zero numbers, right? So we'll reconstruct the equation there. So what happens when we reconstruct the equation? We get exactly 5 times y plus negative 5 times z is equal to negative 2. But then the value of z we have already obtained. The value of z is equal to negative 1, right? So we can eliminate the z from here. So we get 5y minus 5 z is equal to negative 2. It's better to write them down. Then we have got 5y minus 5 times negative 1 is equal to minus 2, right? And now we won't jump any step, right? So 5y plus 5 is equal to negative 2, and then that will give us 5y is equal to negative 7. And from there, what we get is y is equal to negative 7 by 5. Correct? So this is the second variable value or the unknown value that we have got. Right? So we have eliminated y and x from the last equation. The last equation, instead of having x and y, we just have z. Minus 3z is equal to 3. That is the last equation. From there, we get the value of z. Second equation, we have eliminated x from there. But we have the value of z already. So we'll just plug that value in. And finally, in the first row, we have got 1, negative 2, 3. Right? So our equation, someone might help me out. Right? So 1 multiplied by x plus, what is it? Negative 2 times y, negative 2 times y, plus 3 times z, right? 3 times z. Oops. Okay. Sorry. Something happened with my pen tip. No, it's working now. Plus 3 times z is equal to, what was there on the right hand side? 2, right? 2. So we get a 2 here. So what is our equation now? Equation becomes x minus 2y plus 3z is equal to 2. This is exactly the same equation that we had started off with. But now we have got the values of y and z. The value of y is negative 7 by 5 and the value of z is equal to minus 1. So we substitute those values here. So instead of y, we write down minus 7 by 5. Instead of z, we write down negative 1. And then we are going to solve it completely. So this becomes x plus 14 by 5 minus 3 is equal to 2. So this would be x minus 1 by 5 is equal to 2, right? Exactly. So x will be equal to 11 by 5. So we have got the solution. So we have got the solution now, right? So what is the solution? The solution is x is equal to 11 by 5, y is equal to minus 7 by 5, and z is equal to minus 1. So this is the Gauss elimination method. Is it clear with everyone? Let's go ahead and like kind of revise the entire procedure once more. We were given 3 equations in 3 variables, right? 3 equations are given in 3. Yes, please. Who is this? Hmm. 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 Coefficient will be 0, isn't it? Can you repeat the question once more so that we have a very short discussion on that? Okay. Okay. So you are saying that in the first equation, instead of the z is not there, it is x minus 2y plus 3 is equal to 2. So what you do is that you take the 3 on the right hand side, because on the left hand side no constant should be there. every term on the left hand side should be a coefficient multiplied by unknown. So all numbers will be on the right hand side. So plus 3 is equal to 2 is same as is equal to negative 2. So what we will write is x minus 2y is equal to negative 2. That is what we will write. Whenever the set of equations is given to us, maybe from the in the question paper or from the real life modeling that you are doing, if we find out that way, we segregate all the constants to the right hand side and all the unknowns on the left hand side. Right, all the unknowns are going to be there in the left hand side. Okay, so here the z does not exist, so the coefficient of z will be equal to 0. So the equation would be x minus twice y plus 0 times z is equal to negative 1. Okay, okay. So let's revise the entire thing once more, right? And try to figure out whether we have understood everything or not properly. Okay, cool. So first of all, the set of equations is given, and in the set of equations, we see that okay, you know what? On the left hand side, we have got. Let me choose a color. Okay, peach. So there is an x variable here, y variable here, z variable here. The constant is on the right hand side. Good. Then second equation x, y, z. The constant is on the right. Good. Then x, y, z in the third equation, constant is on the right. Good. Now what we do is that we look at the equation and the coefficients, using the coefficients, we write down the augmented matrix. The augmented matrix 1, minus 2, 3, 2 for the first equation, second equation, third equation, and so on. And we have highlighted three different numbers here, which are there in the lower triangular region, right? There are three numbers which are there, which are written in the lower triangular region. So we are trying to our aim is to get those numbers equated to 0. We want those numbers to be equal to 0. So 3 has to be equated to 0, 2 has to be equated to 0, 1 has to be equated to 0. We made 3 as equal to 0 by using R2 as R2 minus 3 R1. Then we made the 2 as equal to 0 with R3 as R3 minus 2 R1, right? And then we made the 5 as equal to 0, right? 5 minus 5, right? So that is R3 minus R2. By using R3 minus R2, we have done it. Okay, so we have got this. This is an echelon form, but it is, I mean, as I said, we are not going, we are going to use the word echelon form in a very loose manner. This is not really an echelon. It happens to be an echelon form, right? But we really wanted the matrix, the coefficient matrix, to be in the upper triangular form. In the upper triangular form, we have got this matrix, and the last row of this upper triangular matrix, of this augmented matrix, the last row has just got one element, one element on the left hand side of the line, right? So that is a z column. That is supposed to be the z column, and one number on the right side of the right of the straight line, which is the constant term. So so what we do is that we reconstruct the equation here, right? So I think it's better that I write it down. We reconstruct the equations. We reconstruct the equations. Now, once we reconstruct the equations, we will get negative 3z is equal to 3 because the coefficient is taken from the left hand side of that straight line. That straight line is there. On the left hand side, everything is coefficient. From there, we take the coefficient. That coefficient multiplied by the unknown will give us the RHS, right? Okay. And on the right hand side, and once we get the value of z, what we do is that we go to the next equation, right? For the second row, we're moving from the last row to the second row to the first row, because we will always have one of the variables, just one and only one unknown, one variable value unknown, right? So once we move to the second row, we get 5x, 5y, right, plus negative 5 times z is equal to negative 2, right? And there we substitute the value of z, right? So since z is equal to negative 1, we substitute this value over there. And finally, we take the first column, first row, right? And then there we substitute the values of y and z. So since y is equal to minus 7 by 5 and z is equal to minus 1, we get this particular uh, value of x. So we get x is equal to, y is equal to, and z is equal to. Cool. Okay. Can I see some thumbs ups in some more thumbs ups in the chat box, right? Yes, Pawan. Good question. Very good question. Now we are going to answer those questions, right? If the last row becomes completely zero, or let's say if there is a zero on beside, on the left hand side of the straight line, but on the right hand side it is not a zero, then what to do, right? We are going to answer those questions now. Okay. Okay. So, very good point brought up by what is that? Pawan. Okay. So let's see. Let's say that we have got, like our augmented matrix to be like this. This value is zero, and this value is zero as well, right? So whatever is there on, okay. So the last row is completely zero, right? And we have got some values here and there. No issues, right? What we want to say is that one complete row is zero. Complete row is zero. If the complete row is zero, then we shall have infinite solution. We'll have infinite solution. Okay. If when we're trying to do this, like row transformation, suppose it happens, it might happen that all of these become equal to zero. In that case, there will be infinite solution. Also, there is another possibility. The other possibility is when we are trying to make things zero, right? We'll look at only the last row, okay? It we get everything zero on the left hand side of the line, but on the right hand side there is a non-zero number, right? So the RHS of last row is non-zero, right? If the RHS is non-zero, while the left side, while LHS is zero, right? If the LHS is zero, LHS zero means all of those numbers are zero. In this case, any guesses? Anyone can guess anything? No solution. Why is it so? Now let's connect the dots. So here, the first case means the row of A colon B is equal to row of A, and it is less than number of unknowns. In this case, the row of A colon B is not equal to the row of A. Because in the row of A, when we're calculating the rank of the matrix, of the augmented matrix, this is counted as non-zero, right? When you are counting the number of non-zero rows of the augmented matrix, this is counted as non-zero. Whereas when we are counting this particular row as uh, a part of A, it is not counted, right? So here this is not counted as non-zero in row of A, correct? Whereas this particular row is counted as non-zero while we are finding out the row of A colon B, right? So the last case, if we have a non-zero number on the right hand side, whereas the entire row is zero, then there is no solution. Whereas if everything is zero, we will have infinite number of solutions. Okay. Is that fine with everyone? We shall now proceed to the Gauss-Jordan method. Yes, I can see a good number of thumbs ups. Okay, thank you. Let's proceed. The x value is what? 11 by 5, y is negative 7 by 5, z is negative 1. Hmm? Okay. So the Gauss elimination method, what we did is that we changed our augmented matrix into an upper triangular matrix, right? This is what we had done. However, when we want to do the Gauss-Jordan method, right? When we want to do the Gauss-Jordan method, let's move to the next page. I think it would be better. Okay. Yes. Let's move to this page. Okay. Yeah. Great. So in the Gauss-Jordan method, some people say this as Gauss, but I use Gauss. Gauss-Jordan method. In Gauss-Jordan method, right? What we want to do is that we want our, the augmented matrix. Oops, the augmented matrix. The augmented matrix. The augmented matrix, we want the augmented matrix to be changed into a diagonal matrix. See, in the previous one, it was an upper triangular matrix, but here we want it to be a diagonal matrix. What is a diagonal matrix? A diagonal matrix is a matrix in which every element except the diagonal entries, the first row, first column, second row, second column, third row, third column, right? Non-zero elements are allowed only on diagonal positions. So diagonal matrix means non-zero elements are allowed only at diagonal positions. I hope you are all writing it down. Okay. Because when you are going to give your attendance sheet, right? At that time, there is there will be a page where you have to paste a photo of the notes that you are taking, right? Okay. Okay, cool. So Gauss-Jordan method is nearly same as the Gauss elimination method, except that in Gauss-Jordan method, what we do is that we look at the augmented matrix and use these elementary row transformations to convert it into a diagonal matrix. Let's take an example and very quickly this time, we won't go through exactly the steps, but we'll try to convert, we'll try to solve this, right? Okay. Okay, so let's look at an example. Mm, which one can I give? Solve. Okay, Gauss-Jordan. Okay, Gauss-Jordan method. Gauss-Jordan method. Okay, yeah, this looks fine. So let's have it as x and then yeah, x plus y plus z is equal to 6, right? And 2x 2x minus y plus 2z is equal to 6 again. Okay, x plus y plus z. No, yeah, okay. And then 3x, 3 plus y minus z is equal to, let's say that this is equal to 2. Okay. Now let's solve this equation, this linear system, right? Now, what is the first step? The first step is to get the augmented matrix. An augmented matrix is represented by A colon B. Or you might as well give those brackets outside them, right? A colon B. So the augmented matrix would be, for the first equation, 1, 1, 1. There is a straight line, vertical line, and 6. Right? Let me get it down a little bit. Yeah. Yeah, that is perfect. So 2, negative 1, 2, and 6, and then 3, 1, negative 1, and then 2. Right? Okay. Mm, okay. Now we need to convert this into, like the diagonal matrix. So diagonal matrix means, see, what we mean by diagonal matrix here is that we want the left hand side to be converted into a diagonal matrix, because then only it will make sense, correct? Diagonal matrix, a matrix has a diagonal only if it's a square matrix. The number of rows and the number of columns have to be equal. And once we do that, we want, let's say, which color should I check? Okay, the gray one. We want this gray, 2, this 3, this 1, that 1, this 1, and this 2. All of these have to be equal to 0. We want all of these to be equal to 0, right? Gauss-Jordan means we want all of this has to be made to equal to 0. The 2 has to be made equal to 0, 3, 1, 1, 1, F2. All these non-diagonal elements have to be made equal to 0. So let's do it, right? Okay. Now, when we are now, we are now experts in elementary row transformations. So let's try to do two row transformations together, right? So the first row transformation that I would want to implement is with the blue pen. That is R2 is R2 minus 2R1, right? And the second one that we want to implement is R3 minus 3R1, right? Let's write down R1. There is no change made in R1, correct? So R1 will write as it is, 1, 1, 1, the line, then 6. R2, that's a blue, right? So this is 0. Then negative 1 minus 2 multiplied by 1. So that is negative 1 minus 2, that is negative 3. 2 minus 2 times 1, that is 2 minus 2, that is 0. We got a 0 here. 6 for the fourth column. So 6 minus 2 times 6, that is 12. So 6 minus 12 is negative 6. Okay. Third row. In the third row, the first one is 0, that is manufactured. We had designed our transformation such that that is going to be equal to 0. The second column, 1 minus 3 times the first row, 1. So 1 minus 3 is negative 2. Negative 1, the third column, negative 1, third row, minus 3 times first row, 1. So minus 1 minus 3, that is minus 4. Fourth column on the right side of the line, 2 minus 3 times row 1 element, that is 6. So 2 minus 18, that is negative 16. Okay. Now you see we have already obtained some zeros, right? So let's highlight what all zeros we have got. We have got 3 zeros till now. See, we do not want to disturb. So what is the strategy? Is that, a very good strategy of getting the zeros is as follows. We can, first get this one, then we can get this one, then we can get the third row second element. Okay, I think I'll use a different pen. Uh, Okay, black is good. So first we'll try to get this second row first element. Then we'll try to get third row first column. Then we'll get third row second column, right? After that, we'll attempt for the second row third column. Then we'll attempt for the fourth, third column of the first row, and then first row second column. So if we come in an anti-clockwise circular manner like this, there is a very less chance of error. Okay. So, but then like this will ensure that we are not going to make any zero non-zero, accidentally. Okay. So we have now the next one is we'll try to make this element -2 in the third row second column as equal to 0. That is the next project that we have. Okay. So before doing that, maybe we can do some more transformations and somehow uh, make these numbers a little bit better looking, good looking numbers, right? So what we can do is maybe the first row we cannot do much, so we'll write that down, right? On the second column, if you look at the second columns carefully, what you can do is that R2 is R2 divided by -3, right? So it will become 0, 1, 0, 2. It looks beautiful now. And the third row, we can divide the third row by again -2. So R3 by -2. So 0, 1, 2, 8. Right? But again, if you are comfortable dealing with fractions and ugly numbers, you are most welcome. Okay? Oh, all right. Now let's see what we can do here. Uh, we want we want this particular element 1 over here to be equal to 0, right? We want this element here to be equal to 0. Now, in order to get this element as equal to 0, Deepak, you're raising your hand. Is there any doubt? So what we did is that we just made these numbers a bit easier to deal with. Look at the second column in the matrix, in the augmented matrix on the top of your screen, right? What do you see? 1, 1, 1, 6, 0, -3, 0, -6, 0, -2, -4, -16. So there's so many negatives are there. So let's remove all the negatives. And you see that in the second row, -3 is there and -6 is there. So what we do is that we divide all of this by -3. The moment we divide by -3, the second row second column element becomes 1, and the second row fourth column element becomes 2. And look at the last row. In the last row, -2, -4, -6, all of these can be divided by -2. The moment we divide by -2, what we get is we get like 0, 1, 2, and 8. Make sense? Okay. Okay. All right. Now let's move on and so I've highlighted this second column element of the third of the third row, correct? So we need this element 1 to be made equal to 0. Now for that, you see we can very easily subtract R3 minus R2. We can do that R3 minus R2. We can change the R3 as R3 minus R2. So let's do that. R3 is R3 minus R2. Correct? Because we already have, like these zeros over here. The two zeros. Oops. Okay. Okay. We already have this 0 here, this 0 here. The gray zeros are already there. The yellow one is what we are going to change. Right? So R3 is R3 minus R2. We are not doing anything with R1 and R2. So 1, 1, 1, 6, 0, 1, 0, 2. We are just changing the last row. We are changing the last row. 0 minus 0 is 0. 1 minus 1 is 0. That is what we manufactured. 2 minus 0 is 2. 8 minus 2 is 6. Right? Now, let's see. Let's, like if we notice carefully, what have we done? We are nearly, we are nearly at our aim, at our mission. Our mission is nearly successful. We have got these four zeros, right? We have got these four zeros. But the last row, we can again, like in the last row, as you can see, there is a 2 and a 6. So we can again, like change the last row a little bit. We can do this as R3 as R3 divided by 2, right? And that will give us the last row to be same as mm, 0, 0, 1, 3. See, the aim is to make things as simple as possible, and it is all in your own hands, right? You can very easily, play around with the numbers and get them correct. Make them like suitable for your use. Okay, so let's identify which ones to change now, right? So we are going to again, like see how to get these things done. So let's see. R R R1. In R1, the third column element is 1. We want to make this as 0, right? And at the same time, we want the element in the first row, second column to be also equal to 0. I've highlighted it yellow. It's there on the top of your screen right now, correct? So we want both of these elements to be equal to 0. Uh, can anyone suggest anything, any operation that we can do? Is there any suggestion from the 100 people out there? Okay, we can extend that idea. We'll change R1 to R1 minus R2 minus R3, right? We are not going to change anything in R2 and R3. 2, 3, 0, 1, 1, 0, 0, 0. But we are going to change the R1. So R1 minus R2 minus R3. So the first column, right? First column. This is the first time that we are taking three rows together, right? In the class also, we have never done this before. So the first column will be 1 minus 0, which is equal to 1. Let's write down 1 here. The second column. In the second column, what happens in the second column? We get 1 minus 0, which is equal to 0. We got a 0 here. In the third column, right? What happens in the third column? 1 minus 0 minus 1, which is equal to 0. We get a 0 here. And the fourth column, we get 6 minus 2 minus 3, which is equal to 1. We'll get a 1 here, right? So this is the final augmented matrix that we get. And with the light gray color, I am highlighting all those positions which have been made 0, right? Is this fine, everyone? Can you understand, right? And now what we do is that we reconstruct the equations. Actually, we do not need to actually reconstruct the equations. We are lucky that all the diagonal elements are 1. So one time for the first, okay. So while reconstructing, let's write down row 1. For the row 1, coefficient is 1. The unknown is x, right? The right hand side is 1. This gives us x is equal to 1. Correct? For row 2, the coefficient is 1, right? Because 0 plus 1 times y plus 0 is equal to 2. This gives us y is equal to 2, right? Reconstructing the last equation, last row 3, we get directly, we can write z is equal to 3, right? So therefore, the solution is x is equal to 1, y is equal to 2, and z is equal to 3. Okay. Did you understand till this step? Right. So here we have got the augmented matrix. After all of these row transformations, we have got the diagonal entries only to be non-zero. There is a diagonal entry 1. This is a diagonal entry 1. This is another diagonal entry 1. Now, we'll look at each of the rows. Let's look at the first row. When we look at the first row, what is the coefficient of x? 1. The coefficient of x is 1. What is the coefficient of y? Right? Okay, so we'll write down x here, y here, z here. The coefficient of x is 1, the coefficient of y is 0, the coefficient of z is 0. So, x multiplied by 1 should be equal to 1, right? Because the last column is the RHS. Okay, in order to understand this, let's go back to the first step that we have done. You remember this particular step, what we have done here? X plus y plus z is equal to 6. That we have written as 1, 1, 1, 6. Right? So the first column here represents the coefficient of x. The second column represents the coefficients of y. The third column represents the coefficient of z. And the last column represents the RHS. Now what we are doing is that we are converting back, the augmented matrix to a linear system. That is exactly what we are doing in both Gauss elimination method and Gauss Jordan method. Right? We are looking at the augmented matrix and we're converting that augmented matrix to the set of equations. And hence we get this particular solution. Yes, absolutely. The row 3 is z equal to 3. 1 multiplied by z is equal to 3. So I can add this, I can write this one here. 1 multiplied by z is equal to 3. Yes, that is right. Okay. All right. So I think we are kind of done with today's class. We extended it through quite a good amount of time. But before leaving, let's revise the entire thing once, right? So, of course, I'll give you the attendance sheet, in the next 10 minutes, right? Let's put up some of the things there. Yes, someone was talking about. Absolutely, absolutely. Gauss Jordan. Okay, we'll do that. No problem. But but let's have a small revision, right, of what we did today, right? So we revised the concept of a linear system, and a linear system is a set of equations having some unknowns, and we convert that linear system into an augmented matrix. The augmented matrix will have m rows. Rows, the number of rows is the number of equations, and the number of columns is the number of unknowns plus 1. The last column after that vertical line contains the RHS values of each equation. And then we were, converting this into an echelon form using elementary row transformations, which was allowing us to understand how many solutions are there. Is there at all a solution, or if there is a solution, is it like infinite number of solutions, or is there just one solution? So, having tested the consistency of a linear system, we wanted to find out the solutions, right? Given that a system of linear equation is consistent, we today tried to understand two different methods to find out the solution, exact solution. These are all exact solutions, no approximation here at all. Exact solutions of linear systems using Gauss elimination and Gauss Jordan methods. Now, the echelon form, in the Gauss elimination method, the echelon form is, we try to convert our augmented matrix into that particular form. But what we really want is we want an upper triangular matrix. An upper triangular matrix is a matrix in which every element below the diagonal are zero. Everything has to be zero. So we took an example and we changed that into an upper triangular matrix. Once we changed into the upper triangular matrix, we reconstructed the equations from there, starting from the last row. The last row is important. We have to start from the last row. If we start from anywhere else, we might be in some problem again. right? Okay. Now, once you have done that, we got the solution, right? By substituting one value at a time. Then we looked at, we looked at the Gauss-Jordan method. In the Gauss-Jordan method, the augmented matrix has to be transformed into not only a upper triangular matrix, but it has to be a diagonal matrix. A diagonal matrix is a matrix in which the non-zero elements are allowed only at diagonal position. Only the diagonal elements can be non-zero. All non-diagonal elements must be equal to zero. And then we took an example, and in this example, we reached this particular form of the augmented matrix where we got a diagonal matrix in the coefficient side, right? And then we reconstructed our equations, right? And while reconstructing our equations, we obtained the values of x, y, and z. Now, when we were, working with the, the transformation of, with the linear transformations of the of our particular augmented matrix, we came across this issue. What was the issue? The issue is that what if the complete row is equal to zero? If the complete row is equal to zero, we'll have infinite solution. Along with that, we had another issue that was raised. What in this case, the the row, half of the row, there is this one element on the right hand side of the line which is non-zero, whereas everything else is zero. In this case, we will have no solution. And yeah, and that's what we had discussed today, right? The assignment, not an assignment, the attendance will be sent to you in some time. It will have three parts: name, your section, and you need to upload a small notes that you have taken in the class, right? And the other two sections will have some questions you need to answer, so that I get to know that you have actually attended the class, right? Okay. Thank you so much.